Section 5, Part 2. In Part 1, or Part A, whatever, we talked about how to use the probability rules from the last section to create charts for a discrete random variable. Let me just add that a lot of these fall into the same, not all, a lot of these fall into the same general category of doing something so many times and looking at how many of those times you're going to get something in particular. Not all of them do, however. In the practice problems, you'll see that there's a nice mixture. There are other probability scenarios. In particular, this one with the racehorse is very nice because it's a variation on the same themes. You've got the slots don't affect one another, but you've got different rules for the slots. And there's a couple of other ones like the coin, and number 5 is good also, which are variations on these themes. You have to use the probability rules, the and principle, the or principle to work out the different results. But they don't necessarily fall into this number of yeses you're going to get when you do something so many times situation. That particular situation we'll talk about in Section 8, and a lot of these examples are of that nature, but not all of them. So just things to be aware of. So having produced a chart like this, or whether it's in probability distribution form here or whether it's in pictorial form, then the logical question to ask yourself, oh, by the way, notice, by the way, that this is our x1, and this is our x2, and this is our x3, and this is our x4, and this is our x5, 5 possibilities. So, don't forget 0. It's the die can't land 0, and the number of heads, the die couldn't land 0, but you could certainly have 0 left-handed people out of so many. So just, watch your labeling. And also notice that unlike a die, which you could theoretically put any 6 numbers, paint them onto the cube, these are still examples of where the bars are consecutive, Go over 1, go over 1, go over 1, go over 1. We'll look at some other examples later where that's not necessarily the case. Remember, the spacing of the bars is significant. 0, 1, and 4 should be 3 apart, for instance, and so on and so on. So, just things to be aware of. For instance, if you labeled the die 1, 2, 3, 4, 5, 10, then you'd have bar, 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 bar over here somewhere, right? So just observe the horizontal scale is what I'm saying. You don't necessarily have evenly spaced possibilities. These examples so far happen to be such. So having produced the chart, either way, whether it's in numerical form here or pictorial form here, 2 logical questions to ask yourself is, where is the center of the chart and what is the spread of the chart? But again, remember, spread and center are not technical terms. They're broad ideas. In particular, we want to talk about the mean and the standard deviation of a random variable. What I seem to have decided, and we'll see how this plays out based on the length, is to do mean in this video and standard deviation in the next video. So first I want to talk about the mean of a random variable. Now, a couple of things to bear in mind. Mean is always synonymous with average, and it is always about balance point. Something else to bear in mind, as I said in the past, something else to bear in mind is that, as I also said in the past, there are different types of means in this course. We've seen 2 already. We've seen the average of the numbers, add them up, divide however many there are. We've seen the average distance from the center, standard deviation. Here's another idea of mean or average, the mean or average of possibilities. X bar, add them up and divide by how many you've got, is the data mean, the data average. You've got 10 numbers, you add them up and divide by 10. You've got 10 people's heights, you add them up, divide by 10 to get the average of those 10 people's heights. Data. We are not now talking about data, we are talking about possibilities. The mean or average of a random variable is the balance point of its possibilities. The mean of a fair die makes sense whether or not you ever generate any data, whether or not you ever roll the die. Much more on that toward the end here. But we are talking about now the mean or average of possibilities. Now, for that reason, remember I said in the past that if you're talking about the data average, or data standard deviation, the stuff we did in section 2. So many numbers in front of you, compute x bar, compute the mean, compute the standard deviation. Then we use the Roman alphabet, x bar or whatever bar for mean, and s or s sub x, whatever, for standard deviation. And I said if we have any other kind of mean or standard deviation that's a little bit more abstract or elusive or unattainable, or in any case, for any reason, is not explicitly the result of averaging or whatever the data together, then we use the Greek alphabet. So possibilities is the key here. Again, the concrete alphabet for the concrete concept, the abstract alphabet for the abstract concept. Now, possibilities, it doesn't get any more abstract than possibilities. So for mean, we are talking about mu. The balance point of possibilities is a mu type of thing. Data average is an x bar kind of thing. The distinction will be very important as we go on. So let's back it up a bit. There are different things you can call this concept, and I've tried to be pretty complete about this. I don't think I've missed out any here. The mean, or average, or expected value, or expectation, or average value of a random variable. Bottom line is the balance point of its possibilities in every sense of the word. Expected value is possibly the worst thing you could call this. Nevertheless, like I've said in the past, these books are not written for you. They are written for teachers, professors to impress other professors, and so they tend to be as jargony as they possibly can. So in an advanced statistics course, you'd see this referred to as expected value. Probably the worst thing you could possibly call it, because it's neither expected nor a value, as we'll see. But nevertheless, people call it that. And if they're really trying to sound like they're trying to impress somebody, then they call it the expectation. Average value, well, it's not really a value, but okay. Mean or average, I think, is to the point. I'm going to tend to use mean, but it's the usual thing. Average is kind of common parlance. Mean is kind of a little bit more sophisticated, but they're all interchangeable and they all mean the same thing. For this reason, if an author is trying to impress somebody, then they tend to call it E of X, E for expected value, expectation. But I'm not going to use this too much except to note that our book and WebAssign may occasionally stray into it. Call it mu sub x, call it E of x. Either way, we're talking about the mean of or average of a random variable. And that is literally the balance point of possibilities. We've talked about this in the past, although we've talked about it for things that were a little smoother, like density curves, but it's the same principle. If this were a sheet of metal of, uniform thickness, if this were a sheet of metal and you laid it flat, it is the spot on the scale here where it would balance. Now bear in mind, that can either be an obvious place if something is symmetric, dead center, 3.5. Ignore the scale, 1, 2, 3, 4, 5, 6. Dead center between 3 and 4 is where this would obviously balance because it's symmetric. On the other hand, there are things that are less symmetric, like our number of left-handed people when we pick 4. Here's a better picture. And where this balances is a little bit more complicated. So that's the idea we're talking about at the moment, the balance point of possibilities. For reasons we'll see shortly, you can also think of it as the long-term average of many repeats, or the average of all possible repeats. We've always got the same three perspectives with probability. the balance point of possibilities with respect to what's going to happen if you do it next, the long-term average of many repeats, we'll talk about that, the average of all possible repeats. So the obvious 3.5 for that die example, you can think of it as the balance point of a fair die, conceptually speaking, in terms of what it's likely to be if I roll it. Or you can think of it as if I average together many rolls of the die, you'd probably get about 3.5. Or you could say that theoretically, if I could average together as data, every possible roll of the die, I would get 3.5. If could, would. You can't, of course. But theoretically, the average of all possible repeats as quote data. So notice that this is the same three perspectives that we have on probability. I'll be a little bit more precise about this as we go on. I've got some supplemental documents here that are not on my notes. As usual, these were designed to be summaries of what we did in class, not the actual first presentation. So I've supplemented it a bit with some extra stuff on these tabs. Now, the concept of the balance point of possibilities makes sense, whether you've got 6 possibilities or something a bit more complicated like this, or what else did I do here? Well, here it is again, many bars. The balance point of this not only makes sense, again, if it were a sheet of metal and you laid it flat, the actual physical balance point of this makes sense as a concept. And you can see that this is pretty symmetric, so it would be pretty close to the obvious place there, right? And a less obvious place if it's very asymmetrical. And it makes sense. Let's see, I don't have any really good density curves here ready to go. I forget whether I have any pictures of the normal distribution here. Let's find out. Well, sort of. So here's the standard normal distribution. So another probability distribution. This is a continuous one. You've got to use area to find probability, but because of the symmetry, the balance point would be in the obvious place. And then, of course, you could have other density curves we've talked about, something that's right skewed, which is smooth, continuous, but the balance point is in a less obvious place, right? So, thought of as the balance point of possibilities, this makes sense regardless of whether it is jaggedy or not very jaggedy, many bars, or theoretically smooth, as in the case of some of our section 3 examples. However, that being said, so it makes sense as a concept, whether it's a discrete or a continuous random variable. More precise than that we can't be without calculus, in particular without integration. So it's not going to happen in a course like this. However, for a discrete random variable, again, there's not a lot more we can say about continuous random variables that we haven't already said, not in a course like this. So I'll show you how this all fits together for continuous random variables in the next section, as much of it as we're ever going to do. But for a discrete random variable where you actually have it listed off in the form like this, everything x can be and the probability of being it with this notation, then what the mean works out to be for a discrete random variable is everything x can be times its probability added together. This times this, plus this times this, plus this times this. So that's what I've got going on in my formula here. First thing x can be times its probability plus the second thing x can be times its probability, well, order of operations, right? Add and then multiply and then add. The last thing x can be times its probability, add him into the mix. So for short, we could say add up every possibility of an x times its probability. Again, a little more longhand for I going from 1 to n. So just for short, adding up every possibility times its probability. Now, as always, for a fair die, it's a little deceptive because the numbers are a little on the nose and the probabilities are all the same. But nevertheless, we can figure it out, right? What is the balance point of a fair die? Well, it is going to be not any major surprise. Again, the perfect probability histogram will be 1, 2, 3, 4, 5, 6, all exactly 1/6 height. So as before, ignore the scales, and this is a little less than ideal down here, but that's the idea. Numerically, then, it would be 1 times the probability of a 1, plus 2 times the probability of a 2, plus 3 times the probability of a 3, plus 6 times the probability of a 6th. Now, if you are going to compute this longhand, then by all means take advantage of that repetition, right? Factor out the 1/6. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. 21/6, 3.5. And sure enough, it's in the obvious place. It is the physical balance point. 1, 2, 3, 4, 5, 6 bar. Sure enough, it's going to balance dead center between 3 and 4, 3.5. Numerically, it works out to be 3.5. So that is the balance point of a fair die. It's also the long-term average of many repeats. More on that in a second. It is the average of all possible repeats. Now, what does it actually represent? Well, let's take a data example. What will actually happen if we roll a fair die 6,000 times and average the results together? The data average, X bar from section 2. 6,000 numbers, all 1s, 2s, 3s, 4s, 5s, and 6s. 6,000 numbers added up and divided by 6,000. The data average X bar of 6,000 rolls. Not the balance point of possibilities, not what we're talking about at the moment. Just get 6,000 pieces of data for a fair die and average that data together. So I picked 6,000 for a reason. It's simple to think about. We will probably get about 1,000 of each number, right? If it's a fair die and you roll it lots of times, then you're probably going to get about 1/6 each, right? So that's what a fair die is, right? If you roll it lots of times, you'll probably get about 1/6 of each number. Probably is vague, about is vague, lots is vague, but 6,000 for the sake of argument, we'll probably get about 1,000 of each number. Now again, there's no guarantees. You could roll a fair die 6,000 times and get all ones. It's just highly unlikely, right? And by highly unlikely, I mean they're independent rolls. The first is 1, and the second is 1, and the third is 1, and the fourth is 1, and the 6,000th is 1. Well, a sixth times a sixth times a sixth times a sixth, 6,000 times. Try 1 to the 6. Try 1 over 6 on to the 6,000. Try 1/6 to the power 6,000 on your calculator and see what happens. One of two things will happen. It either will decide that it doesn't like it at all, or it'll give you 0. It's not 0, but it is cosmically close to 0 as far as the calculator, which can keep track of 100 decimal places, is concerned. It is close to 0. It's not even 0.9901. It's very close to 0. Calculator gives up and calls it 0. Of course, it's highly, highly unlikely that a fair die rolled 6,000 times will give you all ones. But strictly speaking, anything is possible when you roll a fair die 6,000 times. You might get 3,000 ones and 3,000 twos. That's a much harder problem, but it's theoretically possible, and common sense tells you it is highly unlikely, right? Anything might happen. There are no guarantees. You might get 5,000 twos and 1,000 fives. Anything might happen, but we're playing the odds. And by the way, if something weird does happen on 6,000 rolls of a fair die, then crank it up to 6 million. I don't care. Eventually, it'll be the same exact calculation I'm going to do with 3 more zeros on everybody. Eventually, things will balance out. This is not an article of faith. This is simply what it means to be a fair die. Or if you want to be mindlessly pedantic about it, there is a 0% chance that it won't eventually balance out. Anything is possible. You could roll the die forever and get 1. It's just infinitely unlikely. So if you are splitting hairs, sure. But eventually, for all practical intents and purposes, eventually we're going to get about 1/6 of each. Let's say that it's happened by 6,000 rolls, because it probably has. Is it going to be exactly 1,000 of each? No, and that's just as important. And if that's bothering you, make it 6 million. If I roll the die 6 million times, it is highly, highly unlikely that I'll get anything other than about 1/6 of each, if it is a fair die. But it's also highly, highly unlikely that I'll get 1 0 0 0 0 0 0 1s and 1 0 0 0 0 0 0 2s, and so on and so on. It's too on the nose. Probably about. Very important. So there are no guarantees. It probably will not be exact. It probably, let's stick with the 6,000. It probably will not be 1 0 0 0 of each. It might be 993 1s and 1,011 2s, and we won't talk about what's probably and what's about. We'll talk about that in section 9. But loosely speaking, probably about 1,000 of each. It is just as important that it will probably be about 1,000 1s as it is that it will probably be about 1,000 1s. It probably won't be very different from 1,000 of each, but it probably won't be exactly 1,000 of each either. So this is very important. We are playing the odds. We don't know what the data average will be. If you get 6,000 1s, then they're going to average up to 1. If you get 3,000 5s and 3,000 6s, then they're going to average up to 5.5. You see what I mean? If you roll a die 6,000 times, then you could get pretty much anything between 1 and 6. By which I mean you can get 1 point anything, or 2 point anything, or 3 point anything. The average of 6,000 rolls could be 5.783. It probably won't be, but it could. Now, could it be pi? No, it can't be pi. It can't be irrational. There are technically only a finite number of things that can happen when you average together 6,000 rolls, but there are no words for the number of them that there are. It's huge. So we get back to that point I mentioned before. You can't technically get any average between 1 and 6, but you can get trillions, quadrillions, an unthinkably large number of different things between 1 and 6. So it's close enough to true to say that the average of 6,000 rolls could be pretty much anything between 1 and 6. 1 point anything, or 2 point anything, etc., etc., etc. It could theoretically be anything between 1 and 6, but let's play the odds. What I've got highlighted here is a specific number. It's going to be one number and not another. So if I look at the data average of 6,000 rolls, it might literally be anything between 1 and 6, but it will probably be about this number. And what is this number? Well, again, we're playing the odds, so that we're saying we get 1,000 of each number, so that if we add them up, again, this is what multiplication is, right? If we add in 1 1,000 times, then that's the same as times 1,000, and so forth and so on, hence times. So if we add in 1 1,000 times, add in 2 1,000 times, add in 3 1,000 times, add in 4 1,000 times, add in 5 1,000 times, add in 6 1,000 times, then this is what we're going to get, right? And then if it is exact, if this is what we get when we roll the die 6,000 times, big if. and then we'll divide by how many rolls we did. Now let's break this up. Everything that follows is just math. It's all exactly equal. So number one, let's break up the fraction. Thing plus thing plus thing plus thing all over 6,000 is the same as first over 6,000 plus second over 6,000, and so on and so on and so on. So I'll just physically break up the fraction. And then while I'm at it, because of the way that fractions multiply, I can pull the 1 off to the front, right? 1 over 1 times 1,000 over 6,000, for instance. Let's take a less generic possibility. 2 over 1 times 1,000 over 6,000. You multiply the tops, you multiply the bottoms, right? So I can go the other way. I can physically pull the 1 off to the front. So it's 1 times 1,000 over 6,000 plus 2 over 1,000 over 6,000, and so on and so on. Well, the zeros cancel, of course, as it were. This is exactly 1/6, and so is this, and so on, and so on. And we are back to where we started. 1 times a sixth plus 2 times a sixth plus 3 times a sixth, etc., which is exactly my definition of mu of x. So this is the balance point of the die. This is 3.5. So where do we arrive at? If we average together 6,000 rolls of a fair die, you might get literally anything between 1 and 6, but the data average will very, very probably be very, very close to 3.5. You see how this plays out? For a large number of repeats, the data average will probably be close to that theoretical mean of the random variable, but there are no guarantees. You can think of the mean of the random variable, as I said, as the average of all possible repeats. And you can think of the data average, x bar, as the average of the repeats you actually do. The average of so many actual die rolls might be anything, but if there's a lot of them, it'll probably be close to 3.5. And that, remember, was 0.2. So all I've justified is 0.2. If you average together a lot of repeats of the random variable, then you will probably get something close to mu of x. But again, there are no guarantees. No one can tell you what large or probably or close is. It just becomes less and less likely it doesn't happen the further out you go. So you want to clear this up a bit. You can think of x bar as the average of the repeats you actually do, and you can think of mu of x as the average of all repeats that you could do. So what we're saying in the end is that the average of what you do pick, as you average together more and more of them, the average of what you do pick gets closer and closer and closer to the average of what you could pick. The average of what you do pick closes in on the average of what you could pick as you pick more and more of them. Now, if that seems self-evident to you, you're probably missing the point. You can roll the die forever. You can roll the die for the rest of your life. You can average together millions and billions of rolls of a die, and you will never make a dent in all possible die rolls, right? Without getting too philosophical, you could roll the die an infinite number of times and still not make a dent in all possible die rolls there could have been. So we're not talking about exhausting the population in any way, shape, or form. If you make a dent in the population, then as we've already seen, there are bigger problems. You lose the independence, all of these formulas collapse. You can no longer use the and multiply principle and so forth and so on. It may not seem relevant here, but it sort of is. So we are taking for granted at all times that however many repeats we pick or do, you never make a dent in what's out there that you could pick or do. So I'll put this all together for you in the following statement, but it just says that you can think of the mean of random variable as the long-term average of many repeats. The more repeats you average together, the more likely it is you're going to get something very, very close to that theoretical balance point. Let's take another example. What is the theoretical balance? Number one, what is the theoretical balance point for that number of people number of left-handers when we pick 4 idea? And then number two, how can we visualize it? So the theoretical mean for this random variable is going to be 0 times 6561 plus 1 times 2916 plus 2 times 0486 plus 3 times 0036 plus 4 times 0001. That's what it's going to be. And then second, what does it mean? So that's what it's going to be. Multiply it together, and we'll get 0.4. Let me just do that on my calculator really quick. Typing, getting 0.4. It works better in class. The point is, this calculation, there are some shortcuts to it, and we'll talk about those, but theoretically, in a future section. But theoretically, that is how you compute it. 0 times the probability of 0 plus 1 times the probability of 1 plus 4 times the probability of 4. Now, before you can say that 0 times the probability of 0 is 0 times plus is 0 times don't care plus, bear in mind that it is 0 the rest of the time. So that, I mean, compared to what I've got unhighlighted here, it is 0 the rest of the time. So it is implicit in figuring out the calculation, even if it doesn't numerically contribute anything. It's 0.4. In the end, is it plausible that if I laid this thing flat, call this tick mark dead center 0, call this tick mark dead center 1, then 0.4 would be about here, right? So in the end, is it plausible that this thing balances at 0.4? Yeah, I'll buy that. Let's think this through logically, shall we? If you focus too much on, let's look at the chart here because it's a little more deceptive. If you focus too much on the possibilities, then you might say it'll balance at 2. But that is failing to take into account that the 0 is very, very heavy and the 4 is very, very light. So it's not going to be anything nearly as big as 2. On the other hand, if you ignore the top and just focus on these, then you might say it'll balance dead center in the... Sorry, cell phone. If you focus too much on the probabilities here, then you might say that it'll balance dead center at 0 because you do have the majority and then some at 0 itself. But that fails to take into account that the 4, although it doesn't happen very often, is very far away from what we're thinking it's going to be. And the farness away, remember, has a pulling effect. Balance is not only about your weight, but how far away that weight is. So the comparatively far distance away of the 4 has a pulling effect. So it's going to be a little bit bigger than the 0 you might guess if you look too much at these. And it's going to be a little bit less than the 2 you might guess if you look too much at these. The bottom line is you can't visualize it from the numbers. It's going to be misleading, which is why I said that it's misleading to look at the chart, right? It's not even all that reliable to look at the picture here, but you can see that it's not going to balance anything like 2 because of all the weight we've got to the left. It's going to be this way. And it's not going to balance anything like 0 itself because the 4, although it doesn't happen very often, has a pulling effect when it does. So it is literally a balancing act, It is the balancing act between how the numbers pull on it and how the weights pull it down. The numbers pull it right to left. The numbers pull the balance point right to left. the probabilities are weighting it down at that location, right? And it's how those two effects balance each other out. Balance is very tricky. Remember, the median of something, we're not going to talk about it in this context, but in passing, I'll note that the median of a probability distribution is the halfway area point. And the halfway area point is firmly here in case 0. But mean is about balance, and it's a lot more subtle. So things to bear in mind. If you look too much at the top row, you're going to be misled as to the balance point. If you look too much at the bottom row, you're going to be misled as to the balance point. It's literally about how those two things balance each other out. Okay? Now, what does it mean? It's the long-term average of many repeats. Now, that is maybe not very conducive to understanding in this particular case because it involves repeating repeats. But remember, it's the long-term average of many repeats. What are we repeating? Pick 4 people, count the left-handers. So it would go something like this. Pick 4 people, count the left-handers. 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 And on and on and on and on and on and stop eventually. And what do you get? 0, 0, 1, 4, 0, 0, 3, 0, 2, 1, 2, 0, 1, 0, 0, 1, 2, 0, 0, 0. The longer you let it go on, the more certain it is that about 65% of them are going to be zeros, 29% of them are going to be ones, 4% or 5% are going to be twos, 3 out of 1,000, 4 out of 1,000 are going to be threes, and 1 out of 10,000 are going to be fours, right? So the longer you let it go on, that's the balance of what you're seeing in that data. Lots and lots of zeros, roughly a third of them are ones, roughly a 20th of them are a 20th of them or so, 5% are twos, not so many threes, almost no fours, right? And if you average them all together, then you're going to get 0.4. So the long-term average of many repeats. Pick 4 people, count the left-handers. Pick 4 people, count the left-handers. Pick 4 people, count the left-handers. Lots of zeros, ones, twos, and threes and fours, most of which are zeros and ones, the occasional two. They're going to average up to 0.4. And the longer you let it go on, the truer that's going to be. Let's take a practical example. Suppose you've got a lottery. And suppose that 5% of the tickets win you $10, and the rest win you absolutely nothing. And for our purposes, there are millions of lottery tickets out there, far more, orders of magnitude more, than you and I could ever pick. We could pick a lot of lottery tickets, 1,000, 2,000, 4,000, 6,000, but we're never going to make a dent in the lottery tickets that are out there. Millions and millions and millions. Okay? That's important. So let's say that there's a lottery out there. There's millions and millions of tickets you could buy. You could acquire. 5% of them will win you $10, and the rest will win you nothing. And let's let X represent the payoff. Now again, I'm talking about payoff. I'm talking about how much money the ticket is worth. How much money is put in your hand when you hand over the ticket. They either give you nothing or they give you $10. I am specifically, explicitly not taking into account how you acquire the lottery tickets. Buy them, steal them, find them in the sewer, whatever. So we're not talking about profit. We're not talking about what it costs you to acquire the tickets. Assume for the moment you can get them for free, or in any case, however you get them, we're talking about payoff. We're talking about how much money is put in your hand when you hand over the lottery ticket. Well, if it's a loser, as Willy Wonka says, you get nothing. You lose. Good day, sir. And if it's a winner, you get $10. So there's a 0.5, 5% are winners. There's a 5% chance it is a winner. So there's a 0.5 probability the ticket is worth $10. And there's a 0.95 probability it's worth $0. You see what I mean? Depending on your point of view, it's either a probability display for what the ticket you actually have is likely to be worth, or it's a display of how all lottery tickets break down. In the end, a probability histogram is like any other histogram. It's just, as I began to say in the last video, a matter of perspective, you know? So it's a histogram for how all tickets break down. If you buy many, many tickets, it's probably what it's going to look like when you make an actual data histogram. Probably. Or if you like, keep it simple, it's just a probability display for what the ticket you have is likely to be worth. There are, again, always those three perspectives. So there's a 0.95 probability, height, that it's worth 0, and there is a 0.05 probability, height, that it's worth 10. Now again, 0 and 10 are very far away from one another, right? So we're preserving that distance in spirit. What is the balance point of this? Well, let's put it this way. It's a lot less than 5, and it's not going to be 0. So that gives you a rough idea what you're shooting for. But it's actually kind of important now, for reasons we'll see shortly. It's a lot more important than you might expect that I can do this calculation in my head. 0 times the probability of a 0 plus 10 times the probability of 10. Well, 10 times 0.5 is 0.5. 10 times 0.05 is 0.5, and this adds nothing, literally. So there you go. Now the mean is in the same, as always, even a random variable mean is in the same units you started with. Whatever kind of thing x is, that's what it is, dollars. So there you go. The mean, the balance point of the probability of a lottery ticket's worth. What a lottery ticket is likely to be worth, the balance point of that chart is $0.5. The horizontal scale here is dollars. So there you go. If this is 0 and this is 2 and this is 1, then this is about 0.5, right? A quarter of the way along from 0 to 2. So call 0.5 about here. This is maybe 1. This is maybe 0.5. So the balance point is about here. Now again, if you focus too much on the numbers, 0 or 10, you might be tempted to say it's going to be 5. But if you focus too much on the heights of the bars, you might be tempted to say that it's at 0 itself, or a lot closer to 0 than it is. So it's the balance of those two effects. It's 0.5. Now what is the actual meaning of the balance point in this case? Well, again, it's the long-term average of many repeats. So if we have a lot of lottery tickets, then on average they're worth 50 cents each. On average, they're worth half a dollar each. The more lottery tickets you have, the more likely it is that their actual average worth is $0.5. Let's think that through. The more lottery tickets you have, the more likely it is that about 95%, 19 out of 20, are worth nothing, and 5%, 1 out of 20, are worth $10. So the more of those you average together, 0, 0, 0, 0, 0, 0, 10, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 10, 0, 0, 0, 0, 0, 0, 0, 10, 10, 0, 0, 0, 0, 0, 0, 0, the longer you let that go on, the more likely it is that 95% of them are zeros, 5% of them are tens, and that data average will probably be very close to 0.5. We could reverse engineer this, of course. The example I do down here is for the dice. So given that 3.5 is the long-term average of many rolls of the die, if you roll the die 2,000 times 3.5 number per roll, well, the larger this is, the truer this is. It won't work for 5 rolls, but the larger the number of repeats, the more likely you are to get something close to the average of all possible repeats. So the larger the number of repeats is, the more likely it is that they're going to average up to about 3.5. So we'll just reverse engineer it. 2,000 rolls times 3.5 per roll. 2,000 rolls times probably about 3.5 per roll is probably about, well, numerically is 7,000. So the average of 2,000 roll, if you add together 2,000 rolls of the die, you'll probably get about 7,000. Notice, by the way, all this does is reverse engineer. 7,000 actual rolls, 7,000 that they add up to, divided by 2,000 rolls, will give you 3.5. So all we're doing is throwing it into reverse. Likewise, we could do it up here. I kind of wish that I had, here it is. So here it is for the lottery tickets. Suppose we cash in 1,500 lottery tickets. About how much money will we get? Well, bear in mind, 1,500 lottery tickets is insignificant to what's out there. 5% of millions, 95% of millions. There is no reason in the world they couldn't all be losers, in which case you get a grand total of nothing. There's no reason in the world they couldn't all be winners, in which case you get 1,500 times 10, $15,000. But probably you're not going to get nothing, and probably you're not going to get $15,000. It's going to be somewhere between them. What is the chance that all 1,500 lottery tickets are winners? Well, 0.5 times 0.5 times 0.5, 1,500 times, which is not much. What is the chance that all 1,500 are losers? Well, check it out. 0.95 multiplied by itself 1,500 times, that is to the power 1,500, is still incredibly small. 0.3400384 something. Still highly unlikely. It's highly unlikely that they're all going to be losers. It's highly unlikely they're all going to be winners. What is highly likely? That about, 150 of them will be winners, 10%. You get away from that, you're getting into unlikely territory. It may not be on the nose, 145, but it'll probably be close to about 10% of these, right? So we can reverse engineer it. 1,500 lottery tickets times $0.50 per ticket. 1,500 lottery tickets times $0.5 per ticket. Well, again, the larger this is, the truer this is. Long-term average of many repeats. It won't work, it won't be meaningful for 7 tickets, but it'll be very meaningful for 7,000 tickets. So, the larger this is, the truer this is. 1,500 tickets times $0.5 per ticket. Well, the units cancel, right? Tickets cancel, and we get $7.50, what's left? Dollars. So if you cash in 1,500 lottery tickets, you'll probably get about $750. And the larger the number of tickets we cash in, the more true this calculation, or the new one, will be, which is what I'm saying below. Will it be exactly $750 and 0 cents? Highly unlikely, but it probably won't be far away either. If you cash in 1,500 lottery tickets, you'll probably get about $750. How probably? How about? We'll worry about that in section 9. But as a broad general principle, it's true. Let's look at the other example. Now again, this one's a little bit contrived because it involves repeating repeats. But the balance point for the number of left-handers when we pick 4 was 0.4. So let's reverse engineer that. What if you pick 4 people 1,000 times? Pick 4, count the lefties, pick 4, count the lefties, pick 4, count the lefties. Do that 1,000 times. How many total left-handed people would we get? Well, 1,000 groups times 0.4 lefties per group is 400 lefties, right? So again, the larger this is, the truer this is. The more groups you've got, the more true it is that the average number of lefties is going to be 0.4 per group. So 400 lefties. All we're doing, of course, is throwing the data average into reverse. Total number of left-handed people divided by the number of groups would be the average number of lefties per group, right? So we're just throwing it into reverse, which is what I'm saying here. Oh, by the way, while we're here, whether it's 0.4 left-handed people per group, or 3.5 on the die, or 50 cents, half a dollar for the lottery ticket, bear in mind what I said in the first place, which is that expected value is a pretty stupid thing to call this, because it's not a value. Take the die. The values are 1, 2, 3, 4, 5, and 6. Those are the values. Those are the things you could get. If I rolled the die and got 3.5, I would be stunned. It literally makes no sense. It's not expected, and it's not a value. What it is, it's an average, right? It's the average of many rolls. A die cannot land 3.5. It is in no sense expected, nor is it a value. Nevertheless, people call it that. Likewise, no particular lottery ticket is worth 50 cents, right? So, again, I will be stunned. I will be, well, there's a 95% chance I'll be pleased, and there's a 5% chance I'll be pissed if I turn in a lottery ticket and someone gives me 50 cents. I mean, 19 times out of 20, I'll be pleased that I got some money I shouldn't have gotten. But 1 time out of 20, I'll be pissed that I should have gotten $9.50 more, right? So no particular lottery ticket is worth anything like 50 cents. It's either worth nothing or $10. Bear in mind, because this thing is so skewed, it doesn't really have enough bars to rise to the level of being skewed, but it is certainly asymmetrical, right? So you don't have a lot of instinct for where the balance point is, but nevertheless, the calculation tells us that it would be there at 0.5. Now, what's the third example? If you pick 4 people, then you're never going to get 0.4 left-handed people, right? It literally doesn't make sense. Probably be 0, good chance of being 1. 0.4 is reasonable as an average, long term, but it doesn't make any sense for any particular group. So I don't expect to get 0.4 left-handed people, and the values are 0, 1, 2, 3, and 4. It's not a value either. So I don't know why people call it expected value, but they do. It's just one of those things that you live with. I just want to clarify that, right? A die can't land 3.5. You can't get 0.4 left-handed people. No lottery ticket is worth 50 cents. We're talking about the long-term average of many repeats. So all that remains to do here is this part right here, which is basically summarizing what I've already said. In so many words, the law of large numbers. Now, different books, I should point out, will refer to the law of large numbers as meaning different things. But that is to say, some books will kind of dumb it down for you. But the technical version of the law of large numbers goes something like this in relatively ordinary English. It says that extreme occurrences eventually balance out. And all the law of large numbers is really saying here is what I said here about 0.2, which is that the mean or average of a random variable, discrete or otherwise, is the long-term average of many repeats. So all this is saying, before I get into the jargon of it, all this is saying is that the more you pick, the more true it is that the average of what you do pick will close in on the average of what you could pick. So think of X bar as the actual data average. Average together so many lottery tickets that you buy, average together so many rolls of the die, average together so many lefties out of 4, several repeats. And then the mu, or the mu of X, is the average of what you could pick, the average of everything that's out there, the balance point, if you like. It could be actual, or it could, well, we'll talk about that in a second. So let's go through the definition here. Now, I'm going to say this in a way that will be handy for the future. We'll talk about populations and samples in section 7. But suffice to say, the population is everything that's out there, and the data is what you actually pick. So draw n independent observations. The independent is vital. Like I said, if you take a chunk out of the population, 30 cards out of the deck of 52, 7 marbles out of a bag of 12 marbles, then all bets are off. It gets much more complicated. But as long as you're not making a dent in what you're picking from, thousands of lottery tickets from millions, thousands of voters from hundreds of millions of possible voters, etc., etc. 6,000 rolls of a die from all possible rolls of the die. As long as you're not making a dent in what's out there, then we've got the independence, remember. Draw n independent observations from any population with mean mu. Let's pause on that. This could be an actual population with mean mu, or it can be the average of all possible repeats. This is only a way of saying that there are different types of examples. There are specifically 2 different types of examples. You could be doing something like rolling a die or spinning a spinner, in which case everything you could pick is all possible rolls of the die, all possible spins of the spinner. Or you could be talking about an actual but very, very large group of things that are out there that you're picking from. Billions of people in the world, hundreds of millions of lottery tickets. So it doesn't really matter whether it's an actual population, the average height of everybody in the world, 6 billion people would be an example. Now again, you could theoretically average together the heights of 6 billion people as data. Add up everybody's heights, divide by 6 billion. But the key word there is theoretically. That is never going to be data. The heights of 6 billion people is never going to be data. So it is a theoretical average, mu. Or it could be the average of all possible rolls of the die, or the average of all possible spins of the spinner, or the average of all possible average of all possible groups of 4, if you had an infinite number of people to pick from, I suppose. So it could be what I'm saying is it could be a theoretical random variable like a die or a spinner, where the population consists of all possible rolls, all possible spins, etc. Or it could be an actual population that is just very, very large. Populations are large. Populations are too much to think of as data. 6 billion people, hundreds of millions of lottery tickets. Theoretically, as data, you could average together the heights of 6 billion people, but only theoretically. It's a mu. Theoretically, you could average together the worth of hundreds of millions of lottery tickets, but only theoretically. It's a mu. So draw n independent observations from any population with mean mu. And again, there's 2 ways of visualizing that, but it's the average of everything out there, whether everything out there is theoretically infinite or just so many that it might as well be. Draw n independent observations from any population with mean mu. The more of them you average together, the closer it's going to get to mu. The more of them you average together, the closer it's going to get to mu. That is everything we've been saying. As n increases, the x bar, the data average of the numbers you actually get. The rolls of the die you do, the lottery tickets you actually have, the groups of 4 people you actually look at, the spins of the spinner you actually do, approaches mu. Now, a word on the spin of the spinner example. It obviously balances it too, right? But we haven't actually done that in any major way as an example. So the average of what you do pick closes in on the average of what you could pick as you pick more and more and more of them. And again, lest you think that this is self-evident, let me just add, long before you make a dent in the population, if that's even possible. You can spin the spinner forever. You're never going to make a dent in all possible spins. You can roll the die forever. You're never going to make a dent in all possible rolls. But on the other hand, you and I are never going to have any noticeable quantity of all the lottery tickets that are out there. You and I are never going to measure the heights of any noticeable chunk of the people in the world. If you do that, you can't. It's too much. If you did do that, you would lose the independence and this whole statement collapses. So in other words, n is large in one sense, but not large in another. You can have a lot of lottery tickets, thousands, but you're never going to have any noticeable chunk of what's out there. You can do a lot of rolls of the die, but you're never going to have any noticeable chunk of all possible rolls. You can average together the heights of thousands of people, but it's still nothing compared to 6-7 billion people out there, right? So long before you've made a dent in the population, if that's even possible. That's what makes this less than self-evident. Obviously, if you get to the point where you've picked everything, then you're back where you started. But that is not what we're talking about. Okay? So clocking in at exactly an hour again, what are the odds? That pretty much covers part 2, the mean of a random variable. And wherever we talk about the mean of anything, you know what's coming up next. So in part 3, we'll talk about the standard deviation of a random variable, which has to do with how spread out its possibilities are. For a sneak preview of that, let's say that this is lottery winnings in dollars. If I make it lottery winnings in cents, then the heights of the bars are going to be exactly the same, but this is going to be at 0, and this is going to be at 1,000, right? In other words, they're 10 times more spread out from one another than they were, numerically speaking. On the other hand, it's only a unit change, right? So it doesn't change anything substantive. It only changes the way you're looking at things. So more on measuring the spread of a chart next time. The standard deviation always measures the average distance from the center. In our case, the average distance from what we've just been talking about, the balance point. And we'll talk about that in the next video. Part 3 of 3 coming up next, one of our longer sections.